thank you again for inviting me for this talk, and I'm really excited to be here. In this talk, I'll try to highlight the unique properties that we are observing in 2D devices and try to connect them with the emerging trends in deep learning and neuromorphic computing. So this work is in collaboration with Professor Mark Hesham and Vinod Sangwan at Northwestern University. It's a very complementary collaboration that we have been pursuing for a while, because my background is more on the circuit and system side, while Mark and Vinod, they work on materials and devices. Okay. So as the interest in deep learning is actually increasing, it is also leading to some very interesting and new application spaces. Some of them are not there yet, but very soon we will see them around us. So one of the interesting area that has caught attention from multiple domains is that if we can build autonomous drones, which are very tiny, but they can carry different networking equipments with them, then maybe in future, we can build something like flying Internet of Things. So these drones will be able to rearrange themselves and monitor their application spaces much better compared to a static sensor. Likewise, there is a lot of interest in developing cognitive assistants, not just simply Alexa or Google Home, which is just simply doing the speech processing, but rather something which can be more personalized, learn about their users, and behave very much similar to a person when we interact with these devices. We are also exploring ways of applying deep learning and AI for agriculture to improve sustainability by better taking care of our crops, by detecting diseases early and getting rid of them so that we can reduce the impact on environment due to agriculture. So through these applications, very quickly, deep learning is reaching to new spaces where application spaces are going to be much faster. They would require much tinier devices, as well as the consequences of mispredictions will become quite serious. So the applications will also become a lot more riskier. And in these environments, an agent will deal with very dynamic environments, not something like character recognition or something very, very trivial as that, but rather the environment may change very rapidly, and one would need to learn and infer these changes and continuously tune your intelligence to attack or understand these changes and handle these environments. So with all of these double-sided challenges, where at one hand we want these computations to be done at very low power, and on the other hand the applications are becoming more riskier, faster, more dynamic, it is leading to a lot of interesting innovations, both from the algorithmic side as well as from the hardware side. So one of the ongoing revolution that is happening in the deep learning is that increasingly more and more non-classical layers are being explored, which are doing a very high order inference multiplications for making predictions. So for example, hyper networks were proposed recently, where the outputs are as a function of input weights as well as application context. And two networks are coupled. One network generates the weights for another one, and then the follow-up network produces an output based on the context vector generated by this vector, this network. Likewise, there is a lot of interest in doing recurrent networks, especially long short-term memories or gated recurrent units, which again are exploiting these higher order interactions among its operands, input weights, as well as history vectors. All of them are being processed together to make a predictions. There is a lot of interest in transformers, and they have shown that they are really suited for tasks such as natural language processing. And again, transformers are also increasingly relying on these higher order interactions. So inputs, weights, as well as different attention vectors are being all processed together to make a prediction. So from these emerging layers in deep learning, we can see that there is a fundamental shift in the way deep learning is changing. We are going to rely more and more on these higher order interactions, and it will not just simply be multiplying inputs and weights, but rather more than two vectors together to produce an output. At the same time, even neuromorphic computing is going through different revolutions. We are quickly reaching out to more parts of the brains and trying to draw inspirations from them. So for example, there is a strong interest in learning from how a cerebellum in our brain works and applying those control methods in different robotics problems. Cells in a cerebellum work kind of differently compared to cerebrum. They have some very unique properties. For example, they can instantly synchronize, their synchrony is transients. So that again requires your computing units to have a lot more rich characteristics than what is available there. So at one hand, our algorithms are quickly reaching out to more and more complex functions. But on the other hand, our technologies are still playing a catch-up game with these ongoing revolutions. So for example, classically, we use memristors or memristor devices for building a synapse. A memristor is typically just a 2-electrode device. So it is very suited as long as we are just multiplying weights and inputs together. But if we have to do these higher order multiplications, interactions that are needed in the emerging layers, then a memristor will not be suited. One would need to break down the entire computations into multiple small pieces and then run them on these memristor based devices. But that will be inefficient because these computations will be partitioned. We may need to do a lot more digitizations because of these partitioning. So this will lead to more inefficient processing in the future. So to overcome these emerging challenges, as well as to bridge this gap on the algorithmic evolutions in deep learning and neuromorphic computing, we have been actively looking into unique properties of 2D materials and trying to develop new devices which can fill this gap, because these devices will have a lot more rich characteristics and they would be a lot more suited to implement these emerging deep learning layers, as well as enable new kind of neuromorphic computing. So I'll talk about mostly 2 devices today that we have been working on. One of them is Memtransistor, which is a unique device based on MOS2, and it's not just it's basically a hybrid of a transistor with memristor. So it has all the non-volatile properties of a memristor, but at the same time, you can dynamically tune the resistance of the device through multiple gate electrodes as well. The second device I'll talk about is a van der Waals heterojunction based on MOS2 and CNT. And I'll show you that how it has some very unique switching characteristics that lends itself to design very simple neuromorphic circuits with a lot more properties built within very tiny circuits. So in today's outline, I'll mostly, I have divided my talks into 2 pieces. One is going to be about synapses, where I'll discuss how we can use different properties of the gate-tunable synapses, for example, to suppress sneak paths, how we can use, how we can actually do inference more dynamically and build more dynamic inference paths, where the inference path changes itself depending on the application complexity and input complexity. I'll also show you how these synapses are a lot more suited for these non-classical and emerging deep learning layers. In the second part, which is slightly shorter compared to the first part, I will talk about how we can design multimode spiking circuits based on these unique 2D devices, and how it can enable different kind of a novel neural encoding behaviors. Okay. So coming to the first part, the device that we have been working as an alternative to a passive memristor is in collaboration with Mark's group. We are calling this as a Memtransistor device. In this device, we make a channel based on MOS2, but it has 2 electrodes, one gate electrode on the top, and second gate electrode can be formed at the bottom. And through these gate electrodes, the characteristics of these devices can be switched in a non-volatile manner. So unlike a typical memristor, the switching, programming in this device happens because of the movement of sulfur vacancies. So as we apply enough potentials between source and drain, sulfur vacancies at the barrier from metal to semiconductor, they can be moved, and they change the Schottky barrier height, which leads to non-volatile programming of resistance in these devices. So we have seen that through these devices, not only we can change the resistance in a non-volatile manner, but we can also change the resistance dynamically by applying different gate controls. And I will actually want to highlight a unique aspect and not to confuse it with a simple one transistor and one memristor device. The key difference that we are finding here is that the gate voltages are not only useful to tweak the resistance of these devices dynamically, but they can considerably alter the learning behavior itself. So depending on the gate voltage, you can accelerate the learning for the same input pulses. Or if you change the polarity of the gate voltage, you can switch the polarity of the learning also. So for the same drain to source input pulses, by reversing the polarity of gate voltage, you can go from depression to potentiation in these devices. So it's not just simply one transistor connected with the memristor device, but rather by combining all the physics into one single device, it's a more compact device, as well as it has a lot more rich characteristics built within it. So there are a lot of benefits of having a device like this for different applications. For example, if we typically do processing with a typical Memristor grid, it invariably leads to different sneak paths being formed. So for example, I'm just taking a very simple illustration. So for example, in this case, let's say we want the current to flow from conductance G12, but what can happen if the input lines are floating, then sneak paths can be formed by connecting, let's say, these new conductances G11, G21, and G22, and that leads to extra current going to the same column, and that causes the output to be erroneous. Although this can be fixed by integrating a transistor with the Memristor devices, but that affects the density of these crossbars, also adds more parasitic capacitance in between, so that also leads to more energy dissipation. And compared to that, using a Memtransistor, we can build a beyond passive crossbar architectures, where not only we will have all the density benefits of a typical passive crossbar, but because of gate voltages, we can control the different properties of the crossbar to suppress these sneak paths dynamically, right? So for example, in this case, we can also play with the vertical and horizontal gate grids, which can suppress some of these conductances as they are if they are forming a sneak path to the column. And by suppressing those conductances, we can control the accuracy of these designs while still being able to build everything in a very compact and dense structure. Right. So we actually played with a very simple crossbar design to analyze the benefit of Memtransistors. So in this case, typically in crossbars, even though the crossbar power can itself be minimized, it can often be hugely dominated by different peripherals. So peripherals can play a very important role in the overall energy efficiency. So we looked into a time and charge domain processing, where we could do a lot more things in digital, which is a lot more energy efficient, at least for peripherals compared to analog. So we looked into an architecture where we can apply inputs not using a typical digital to analog converter, but rather using a timing pulses. So an input can be encoded as a pulse width modulated signal, and these inputs can be applied to the different memristors on the crossbar. And along the column, these Memtransistors, they push charge as long as the input pulses are active. And because of this charge accumulations at the output, a natural dot product of input with the weight vector that was stored on the column is actually gets accumulated at the charge end. Right. Along with these input pulses, we can actually also use them to suppress sneak paths. So for example, whenever a timing DAC will be inactive, we can use the same trigger to also cut off all the paths along the way by applying these voltages along the gate voltages here, and that will help cut down the sneak paths, right? And we still have the top gate controls left, which I will come later on. So overall, it will allow you to not only control the sneak paths, but also do something a lot more interesting that I'll slowly come to. So we analyzed an architecture like this, and compared to a typical Memristor crossbars, we saw that even if we can scale the crossbars to very, very large dimensions, it doesn't actually introduce significant processing errors. And all the processing errors that are happening here are happening mainly because of the non-ideality of your peripherals. For example, limited gain of these op-amps, or in the charge accumulators, which are basically accumulating the charge, but not really happening because of the crossbar itself. So that allows you to build a lot bigger crossbars, which will minimize the amount of peripherals and help us to balance this budget that we spend for crossbar processing versus the budget that we allocate for peripheral processing. Right? For a small crossbar, the budget that we have to spend for peripheral processing might be significant, and that becomes one of the source of inefficiency in a typical Memristor device. Right? In addition to that, we can actually also exploit the gate tunability of these devices to make our inference more dynamic. So typically, when we operate a deep neural network, all the weights as well as the connections from neurons to the next layer neurons are all static. No matter how complex our input is, the inputs always pass through the same stages of different hidden layers until it reaches at the end where a prediction can be made. But now, because we have gate tunability of the synapses, we can actually design a more dynamic inference path. So depending on the input complexity, as well as the high level features of the input, we can change or morph this network on the run. We can disable a couple of these neurons. We can control the synaptic strengths of these neurons so that we can do inference a lot more efficiently compared to a typical static pipeline. So we actually exploited this feature. And a unique aspect here is that because we have the gate tunability in these devices, it allows us to do something we are calling as a soft gating of the synapses. If we want to do something very similar with memristors, then we have to either entirely cut it off because it's a passive device. So you, in order to do something similar, you have to apply a hard gating where you can entirely cut it off. But that leads to significant increase in training time because now your training becomes very complex. It has more combinatorial optimization objective, and that limits the application of those techniques to more realistic and complicated processing tasks. Meanwhile, here, because we have the gate tunability, we can softly suppress or change the strength of these synapses and still have the whole network differentiable, which can learn using typical algorithms, and it will not increase the training load significantly in this case. Right? So the scheme that we exploited, where we are utilizing these features of Memtransistors, is that we are learning from the input that is being applied to a layer, projecting it to a very simple set of adaptation neurons, which are basically controlling the synaptic behavior of the entire grid, right? And in order to minimize the overhead of these adaptation neurons are shared for multiple columns. So essentially we don't have as many adaptation neurons as the output neurons, but much fewer than them. But by using these adaptation neurons and applying their potentials on the gates of these main synaptic grid, we can dynamically change the nature of these synaptic grid for different computations. Right. So this allows a more tight-knit co-optimization of learning algorithms as well as technology, because now the algorithms are being also adapted to the new features technologies are exposing, and this design is not just single one way where given an algorithm we are simply looking for the best technologies, but rather we are going back and forth and trying to merge both of them much more efficiently. So in this case, the mechanism happens that when we apply the input, the adaptation neurons take these inputs first, and we can disable the main neurons based on the backgate voltages. And these adaptation neurons will predict what should be the synaptic weight of this entire grid, or basically what should be the synaptic scaling factor for this entire grid. And that factor will be applied in analog domain at the gate voltages itself. And then after that, the entire input can be processed from the main grid to produce the net output. So, but by dynamically modulating the strength of these synapses, we can save the bias energy while making sure that the accuracy of the predictions is not degraded because of this. So we looked into these applications on tasks such as CFAR10 classifications, and applied a different number of adaptation neurons, and also wrote algorithms which can account for these unique properties of Memtransistor devices. And as you can see that in this case, that these adaptation neurons can pick very high level features of inputs. So note that these neurons are not really reading the entire images, but much filtered version that is being passed through to them from the preceding layer, and they can use these very highly abstract view of the input and use that to control the strength of different parts of the network, which is being shown here as a function of adaptation neuron strength. Right. So when we do something like this, we saw that by adding more adaptation neurons, we can adapt better, and we can save up to 20% energy compared to a grid which doesn't do these similar operations on CFAR10. Right. So not only we can make more complex grids, we can suppress sneak pass, but rather we can also develop more beyond passive crossbar architectures, which can dynamically morph themselves to different synaptic strength as well as different behavior depending on the input characteristics, and make better use of the energy for doing these computations. Right. Likewise, the benefits of Memtransistors are not just limited to typical layers, but they are also useful for emerging layers. So one of the layers that I mentioned is a hypernetwork where multiple entities are being processed together. And typically these networks exploit quadratic multiplications. And here in Memtransistors, because we have multiple gate voltages, we can control the synaptic strength based on these gate voltages, and we can do these quadratic multiplications right in one device itself. Right? Otherwise, if we are using memristors, then we have to break these computations into multiple parts that requires more ADC operations, more charge integration operations, as well as may require more digital operations to be added on top of that. Right? So by collapsing everything into one crossbar cell, we can avoid partitioning of our computations. We can be very much aligned with the algorithms and their benefits, as well as minimize any extra work that we need to do because our technology is not capable to do those higher order computations. Right? Likewise, we saw the benefits of Memtransistors even for LSTMs and GRUs, where Hedman product is utilized to exploit history for making predictions, and there also we can exploit these vertical and the horizontal gate grids to couple to crossbar in a more interesting manner, where we can apply inputs from one crossbar to the another one through the gate grid itself to avoid all the ADC convergence in between, and that again saves significant amount of energy in these cases. Right? So given these devices are multi-terminal, a lot more interesting things are possible, and a lot more unique architectures can be easily developed for these applications. Right? And because we are minimizing any extra workload, it naturally leads to much better scalability of Memtransistor-based grids, where we require much fewer ADC operations, we require much fewer digital operations, fewer DAC operations, little bit more DAC operations, but because these DAC operations are based on timing DAC, the overall energy efficiency is still much better. And overall, for these emerging layers, Memtransistor grids, they perform much better. In this specific case, they consume 15 times less energy compared to memristors, and lead to a lot more benefit in this case. Now, in the last 5 minutes, I'll quickly go through the other part of these devices and how they can also benefit the neuromorphic computing. So one of the interesting properties of these devices is that we can utilize these materials, MOS2 and CNTs and other 2D materials, to build very tiny and compact van der Waals heterojunctions. And these heterojunctions can have some very interesting properties. For example, they can have an anti-ambipolar behavior. So in this case, when we switch the gate voltage in these devices, the current scales up, and then it comes down, and then it starts to increase up again. At the same time, because these devices are so thin, they can easily have multiple gate voltages, and we can tweak these characteristics based on gate voltages. And we saw that the characteristics that these devices are showing, they have a very close correspondence to different ion gating that has been explained by the Hodgkin-Huxley model. So especially the ion gating for sodium channels it has a very similar behavior, where the conductance channels opens quickly, and then over time they are slowed down. And because we can obtain these characteristics in one single device, it naturally allows our neurons to be very simple. So we actually looked into a very simple circuit, which only requires 2 transistors and one of these devices and a few passive elements to build a spiking neuron circuits based on the Hodgkin-Huxley model. And here, by exploiting the anti-ambipolar behavior of this device, we were able to design some very simple circuits which had a very simple spiking that has been predicted by the simulations of the model. At the same time, because these devices are gate-tunable, they are not just spiking neurons, but they are multimodal spiking neurons. By simply changing the bias voltages between top gate and the bottom gate, or by coupling them through some very simple circuits, we can dynamically change the coding behavior of these neurons. So they can go for the same input, they can go from constant spiking to phasic spiking to bursting, class 1 spiking, and dampen tonic bursting. So they can easily reconfigure their oscillatory behavior into different modes for the same input by simply playing with their gate voltage biases. And in the beginning, I talked about interest in alternate brain structure and the other important brain structures for applications such as robotics. And it has been found that in some of these structures, for example, in cerebellum, such kind of a coding behavior where you can dynamically switch from one coding pattern to another coding pattern is very crucial. This is something that allows us to maintain our balance or react quickly when we touch something hot. And those incidences immediately switch the neuron coding behavior. And now now these mechanisms can be achieved in very simple and tiny circuits, thanks to interesting characteristics of these devices. So overall, there are a few takeaway messages I just wanted to highlight. One is that as the deep learning algorithms and neuromorphic computing science is evolving, it is also requiring more rich and higher order interactions between neurons and synapses. Currently, there is a gap into what technology can offer. And the current way is to break down these computations into pieces and do them part by part, given the technology limitations. But that would be inefficient because it will require more workload as well as more intermediate steps. We have shown that 2D materials have some very interesting properties, both for synapses as well as for neurons to address this gap. And they are gate-tunable, and they can be used to address these applications very well. Now, thank you so much for your time.